Okay, so let us continue from where we left in last class, which is trying to understand how we define a standard atmosphere. So, this clearly is actually a model of our standard atmosphere. The real atmosphere may actually not necessarily be exactly a replica of this, but this is what is already observed. So, this is not something which has been just created out of fiction or somebody's imagination. It is of course, I mean done through years of experiments where people launch these weather balloons, which actually have this radio sonde equipment, which gathers data regarding your pressure, your temperature, and it sort of profiles your atmospheric boundary layer or your entire atmosphere for that matter. So, this is a model of atmosphere. Okay. Yeah. And as we see, the first thing is that we experience when we start from sea level and we go up to 11 kilometer, we have a negative lapse rate, which means my temperature actually continues to decrease as we go up. And you can see that lapse rate is defined like this, the rate at which my temperature changes basically, okay, with altitude, and that is negative for the first 11 kilometers. And then we have from 11 kilometers to up to 25 kilometers of altitude, we have actually a isothermal zone, which means isothermal, iso plus thermal, thermal is your temperature, means same temperature. So, you have a zone of same temperature here. Okay. So, you see this is called isothermal layer, which means in this area the temperature does not change. Then after 25 to 47, we have now again positive lapse rate, my temperature again increases, so it comes back to almost similar values as what you would actually experience at sea level. You can see it is like if my standard temperature, room temperature is 288 kelvins, I mean at 47 kilometers height, I almost reach similar kind of temperature there. Okay. And then again there is a small isothermal layer, from where now we will actually see a more dramatic reduction in temperature, and again you have a strong negative lapse rate, though this is slightly lower. My earlier lapse rate was 6.5 kelvins per meter rather, here it is minus 4.5 into minus 3 kelvins per meter. So, you can say 4.5 Kelvin per kilometer, I can multiply with 1000. Likewise, here minus 6.5 kelvins per kilometer. So, if I go 1 kilometer, I will see a temperature drop of roughly 6.5 kelvins. Okay. So, this is fine, I mean this is how my temperature changes, but the more important thing is that beyond temperature, I mean I am more interested about knowing how my density changes, because that is the key parameter which governs the performance of my unmanned aerial vehicle. Okay. So, to understand that, I mean we will have to go a little bit into the basics of fluid mechanics. Some of you may have forgotten that long back. So, it is a very simple derivation. More importantly, I mean the physics is very simple, which I am sure you will be able to follow, and all you have to do is basically sort of remember the formula in mind. I mean you do not have to learn it by heart, because I mean as an engineers now we do not actually have to memorize things. I mean there is world of ChatGPT, you can get any information you want from anywhere, but we should know what and how to apply and where to apply. So, usage of the formula is more important, understanding the concept is more important. Almost all exams, I mean at this level we normally organize them as actually open notes, open book kind of exams, where you do not have to come memorizing things. I recommend students to actually come prepared with a cheat sheet with all the relevant formulas written in that, so that you do not have to look at your notes also, to save your time basically, because it is all about application. It is not about, I mean remembering things. Okay, I can memorize so many things, how does it matter? I mean I can simply ask my phone and I will get answer to pretty much everything, right. So, that is how it is, but now we are sort of entering into the age of application, where we have to understand what concept could be applied where. ChatGPT will not be able to help you with that. Okay. So, that is where I mean the human intelligence is going to be important and not so much of artificial intelligence. Alright. So, now we will start with a very basic thing, where we take the basic hydrostatic equation, means how my pressure would actually vary. So, you imagine I mean a tank is full of some fluid, let us say water. So, you can understand that your pressure will increase from top of the surface to the bottom, okay, and the pressure will be proportional to the weight of water which is above you, right. So, that is why I mean the moment you start going deeper and deeper into water, your pressure actually rises significantly. Okay. So, I mean you can sustain pressures up to certain level, and beyond that I mean you require special equipment and accessories to handle such kind of high pressure. So, we assume something similar, but instead of looking a whole tank of water, we are here talking about an infinitesimal tank, really tiny tank, and we want to understand that how my pressure is going to vary from say one location to another location. Okay. So, if I see my pressure is here P and this is a small infinitesimal volume that I am looking at. Okay. So, I can draw a cuboid which basically represents this. So, I am saying that I mean my pressure on the bottom surface is let us say P, then how does my pressure on the top surface be? So, this is basically a small cubical rather volume which I am looking in somewhere inside the fluid, and my pressure would be varying. So, it is not necessary that I mean we are looking at the vertical profile, it is just general profile. So, what I am saying is that because of different boundary conditions, underlying conditions, my pressure is varying from every point to point. Like we imagine the tank, my pressure is varying from top to bottom, right, or bottom to top, either way. So, we say that I mean if I move across a distance of this hg, d of hg, which is my height change, right. Okay. So, my change of height in atmosphere in this case, if I move through that kind of distance, my pressure is also going to change from original P to some P plus dP or delta P. So, my pressure changes from P to some P plus dP, okay, because I am moving across an infinitesimal means very small differential change, okay, smallest possible change I can look at. So, if I change my height by that much, my pressure of the fluid is going to go from one value to some other value, and that other value I am simply representing as its same pressure plus some new change pressure, and that change pressure is my dP, right. So, if I look at this and imagine the gravity also acting on this, because there is a weight of the fluid which is contained inside, in this case for us it is air not water. So, how does it change actually? So, to assure equilibrium, it should be P equals to, which is my pressure at the bottom, must be equal to pressure at the top plus this extra differential pressure and the weight of the fluid, and weight of the fluid is simply what? Volume into density, right. So, density is what? I mean density is your mass per unit volume. So, I know density of air. If I take the volume of air contained inside this cube volume, I can simply, so rho into g into dH g, right. So, this rho g is my mass and dH g is because I am talking about pressure change, not about I mean the force change. That is why I am not multiplying with the whole volume, I am only multiplying with the distance across which that is there actually, because the surface areas will be same for both the sections actually. So, that is why we are multiplying rho g into the distance dH. So, if I look at that, I can see that my these two p's are same, I can cross them over. So, my dP, the change in pressure is purely because of the weight of the air, right. So, which can be written like this, if in a simplified form, where I assume that across this small infinitesimal change of height, my acceleration due to gravity does not change, it is a fair assumption. So, this becomes my basic fundamental equation, which is dP equals to minus of rho g naught into d of h g, okay. And what was my h g? We have defined h g as the geometric altitude change, which is height above sea level, okay. So, above sea level how much I am changing, and anyhow I am talking about going from one point to another point. So, I do not have to worry about radius of earth and all those things, I simply see the delta h, the change in that. So, this is my dHg. So, dHg is change in geometric altitude, right. Okay. So, let us see what we can do with this.
So, this fluid element is any fluid element which is in air.
This is air itself. Okay. So,
because the pressure
this is true about any fluid element. This particular derivation is true about any fluid element. So, any fluid element means, I mean, it could be element inside a water tank, it could be an element inside some other flow channel. Okay. So, it could be anywhere, but for us it is basically the atmosphere.
So, the pressure in the bottom phase is lesser than the pressure or more than the pressure on the top, because the dP is negative.
dP is negative, you are saying, right? Yeah, yeah.
So, the pressure in the bottom will be more than the pressure on top, because it is reducing.
Yeah, of course. Yeah, so see, as you go up, I mean, the pressure keeps on decreasing, right? Okay, so that's what it is actually. Okay, so no, the pressure decreases only, right? Yeah, because at the bottom, I mean, all the see the whole 11 kilometers of atmosphere is actually putting load on you. I mean, actually even more than that, right? Okay, not just 11 kilometers. The entire thing is actually putting the pressure there. So your pressure is maximum here. It will keep on decreasing only, right? Okay. So now with this relation, we will see what all we can get. Also, we will use your ideal gas equation. Okay. Pressure equal to rho RT, rho being your density, and that combined with the equation which we have got, which is my change in pressure with height basically, okay, how my pressure is going to vary with height, and I can combine these two equations and I get a relation. So, I divide this, so I can call this equation 1, this is equation number 2, and divide 1 by 2, and I easily get this relation. Okay. So, now this relates pressure with height directly, okay, and other things being constant. Okay. So, if I integrate this equation, what I get is that dP by P, which means this will give me log natural of P. Okay. So, if this integral will give me that, and G naught by RT is constant, I take it out and I get this. So, this in effect tells me a relationship that my P by P1, so pressure at one altitude versus pressure at other altitude actually is exponential function. Okay. So, it varies in an exponential manner, and in this now we can also substitute the effect of lapse rate, okay, which is this. So, lapse rate is basically a linear equation, right? I mean, we saw, so this is just an equation of a straight line. This variation is linear as we go with altitude, especially up to 11 kilometers. Okay. So, this right now, I mean, I am applying primarily, say, because most of my aerial vehicles are going to fly in this domain. Okay. So, this is what I will do. If I have to look at that, then I mean, I have to go back to that standard atmosphere and see if I am operating at some other altitude, for example. So, if I go back here for a moment, so if I am operating here, yeah, then I already know this is the isothermal layer. So, I have to use different set of equations and things to find. But if I see 11 kilometers, 11 kilometers is probably 11 kilometers is 35, close to 35, which is fairly high altitude. I mean, even male HALE UAVs would operate up to this layer only, okay, or this level only. Only HAPS kind of UAVs would probably operate somewhere in this zone, like around 40 odd kilometers actually, or more. So, only then I mean, I have to go back and relook at this and see how my temperature is increasing, so how my density is varying. So, this will be a slightly different problem. Otherwise, we are mostly fine with this. Okay. Anyhow, I mean, you do not have to know this mathematics, because this is a standard thing, it is available in books. There are tools available, softwares available, which models the entire thing for you. I can simply look it up, like I said, I mean, I do not have to memorize things. Okay. I simply look it up in on internet, and I can find a calculator in which you have to just simply put the altitude, put the additional temperature beyond your standard atmosphere conditions, and you will get all the parameters you require. Okay. So, you will get the pressure information, you will get the density information, and so on. Okay. But we must understand, I mean, how these tools are developed. Okay. So, that is important part. So, that is why we are introducing all these ideas to you. So, we get that relation, and just by playing along with all that, I mean, I can, and using again back my ideal equations, I will get these 3 relations. Okay. And these 3 relations are adequate for me to determine all the key parameters, how it varies in my lower atmosphere, where most of my UAVs are going to operate. Okay. So, now if you see, the key parameter actually which I know for sure and I can easily calculate is my temperature variation. So, if I know my temperature variation or temperature currently at the sea level, using the lapse rate I can easily know the temperature at a higher altitude. So, I will be able to know T and T1. Once I know T and T1, I can get the relation between my pressure at sea level versus pressure at a high altitude, and similarly density at sea level versus density at higher altitude. So, that is the easy thing. So, these three relations are adequate for me to get all the key parameters which would govern my performance. Now, other than density, which other parameter is relevant for me when I look at my performance directly? Why is density important? Because lift, right, my lift, drag, pitching moment, everything depends on density, right. So, my lift equation you recall, what is it, half, right. So, CL is a parameter which is feature of my geometry, my shape, airfoil shape, etc., but this is my atmospheric parameter which directly affects my lift. But beyond this, which other parameter is important among pressure? So, density we have already identified. Among pressure, temperature, gravitational pull, which other parameter do you think would affect my performance? Temperature. How?
As we move up.
Yeah.
So,
but I am already accounting for change in density because of temperature change. What else will it affect?
Compressibility. Speed of sound.
Speed of sound, exactly, yes. So, my temperature actually also determines my speed of sound. Yeah, how we will see. I mean, so towards the end of the these slides, we have expression for calculating the speed of sound also. So, speed of sound is not also constant; it is a function of temperature. Okay, so if I go to very low temperatures, I mean there will be a minor variation because your temperature variation would not be very dramatic. Okay? Your temperature is varying by how much? You see, it is varying by barely 60 odd kelvins across this layer, right. So, 60 kelvins, well, it may vary by some small factor, but not a whole lot, but it may be important. Okay. So, I have to keep in mind that when I am looking at my compressibility effect, if my speed of sound changes, which means my aircraft's Mach number will change, and it is not my speed, it is my Mach number which determines my behavior. So, that is something which I have to be aware of, especially when I am trying to make a UAV which will fly at very high altitudes and so on. Okay. So, these are the three key things. So, in all these variations where I want to look at the variation of my pressure, variation of my temperature, variation of my density, right, with altitude in particular, sea level values they act as my reference point, okay, because they are the standard. So, I will define that my standard atmosphere, for a standard atmosphere my sea level density is so and so and so. So, these are the numbers which represent the standard atmospheric condition as per this international standard atmosphere, okay, that is the name ISA. So, for ISA conditions my pressure would be what we call as nearly 1 bar, 1.01 10 to the power 5 Newton per meter square, which is also called pascals. If you want to go in the imperial units, it comes in pound per feet square. My density in SI units is 1.225 kilogram per meter cube. This is something which you have to more or less remember, because anytime you have to do calculation, you will quickly put this number. Yeah. So, it is a very small number to remember, and once you start using it, you will not forget it that readily. 1.225 kilogram per meter cube. Standard temperature is 288.16 kelvins. Okay. So, these are the standard sea level reference values. Now, any value I have to calculate, I would use this as a reference and use these three formulas, and I can. So, my T1, P1 and rho 1 would become sea level reference values, and correspondingly I can calculate my T, P and rho, or yeah, right. So, we have used actually P1 as a reference. So, T1, P1 and rho 1 are my reference values, which we are calling here as PS, rho s and Ts. So, subscript S is basically saying sea level, okay. This small s is basically sea level, okay. And yeah, so that brings us to any questions on this. So, it is clear now. Yeah. What I have to do, I mean, if I have to find out prevalent conditions at any altitude of operation, I simply have to start with these reference values, and first thing I will do is that I want to say find out my performance or my parameters at say 3000 meters of altitude. So, I will simply put this h minus h1 as 3000, right, multiply that with lapse rate. Yeah. So, h minus h1 is my delta h only. Yeah. So, my height becomes 3000. So, my reference is already sea level, which is 0, right. So, h is 3000, h1 is 0. So, the difference of these two is actually 3000 meters. So, I will use that multiply with my, so this is 3 kilometers, right, and what is my A is minus 6.5. So, I will multiply this with minus 6.5 into 3. So, it is 18, 19.5. So, my 19.5 kelvins is the change in temperature. So, if my T1 was say 15 degrees or whatever, minus 19.5 will give me my temperature as per international standard atmosphere at 3000 meters. Yeah.
From Leh.
Yeah.
So that H and H minus 1, that DH will change because the takeoff level will not be sea level.
No, no. So, I mean, finally, you want to get the point at the altitude where you are currently at, right? So, you say you are launching from 3000 meters or say 4000 meters, and then you are going to go to further, say up to 5000 meters you are going to operate. So, you will first calculate the conditions at 4000 meters, right? So, that also you will use sea level as a reference, then 5000 also you will use sea level as a reference. That is the easy thing to do. Yeah. So, that way I mean I can, once I get the 4000 values, I can use that also as a reference and then calculate things based on that by using 1000 as extra change. So, that also is perfectly fine, but the convention is that you will remember sea level values readily. I mean, I do not remember, I mean, what is my value at 4000 meters, right, but I know sea level density, sea level temperature, I know very easily. So, it is easier to always keep that as a reference to calculate any values, but yes, I mean, if I know my conditions at a particular altitude and then I want to see how it is going to change to another altitude, then I can use that value as long as I know the reference value at 4000 meters, for example. But what is conventionally known is sea level, that is why I am saying that. So, here I mean I will do that, so I get the temperature change, right. So, I get this new temperature and I know the other temperature values and use all that here, where your R and other parameters are all standard parameters basically. So, R is your gas constant, which I think is given somewhere, let me see, or maybe not. So, you can just look it up on internet. I mean, I forgot to put that actually as a reference value because that is also standard your universal gas constant, right. So, yeah, 287 some joules per kg, something like that. So just use that. Yeah, I mean I have not used these equations for really long time, so forgotten them. Yeah. So these things you can easily look up and get the values for. Okay. Yeah, and in this A you see A is my, what is A? Lapse rate, right. So that is already minus 6.5 is a standard thing for this. Okay. So fine. So now based on this definition of international standard atmosphere, we also tend to define my altitude based on pressure, density and temperature, which means, so when you say pressure altitude, you say you measure the ambient pressure and look up at ISA table and find out the corresponding altitude. What does this mean actually? What is the meaning of this statement? So now we are introducing actually a new idea of my height. So there is a geometric height, right, which we are calling as Hg, which is actual height above my mean sea level. I can also define my height from my center of the earth, does not have any relevance except for calculating your g, but other than that it does not mean anything to us. But beyond that, when you are operating an aerial vehicle, how your vehicle is going to perform would depend on the kind of pressure, static pressure you have, density you have. So based on those numbers, I can directly try to sort of relate that to what it corresponds to my standard atmosphere. So as per standard atmosphere, international standard atmosphere, let us say if I am looking at a particular location which is at a say maybe a 3 kilometers height, okay, so 3000 meters. Okay. So I want to know what is going on at this particular altitude or how the performance is at this particular altitude. Okay. So I can use my table data and calculate this value. Other way around is that I am at some height, I do not know what height I am at actually right now, but what I can know is that I have some device by which I can measure the pressure, some device which can give me the density at that location and temperature at that location. So I simply take that number and reverse calculate things for me. Okay. So try to get corresponding height for which in my ISA table it will actually give me the same value of density or same value of pressure or same value of your temperature. So in this case we are defining now our height based on my perceived pressure or density or temperature. Am I making sense? Yeah. Everybody at the back? So same way, so what you do is that you simply measure your ambient pressure. I measure my pressure and I find some number. Now what I will do? I will go and put this number in my table or I just look at the table and see, okay, where this pressure comes. oh, this pressure comes at actually 3500 meters. Now question is why this pressure and my ISA would be different. Why? Because my ISA says my sea level temperature, pressure and density, everything is at one value, but in reality it is not like that. So one day we have, I mean, temperature here actually at 25 degrees, another day, I mean, bright sun comes out and it will be 40 degrees, you do not know, right. So because of my local weather condition, my local temperature, pressure, density, they all vary quite a bit. Actually this we may not normally realize, but when the humidity becomes very, very high, I mean, especially in Kanpur we experience such high humidities, my density changes dramatically and my oxygen content in air also changes dramatically. So as a human being, we also feel some kind of suffocation, that I mean, I am not getting enough oxygen. Same problem happens in Leh Ladakh. When you go there, I mean, it takes tremendous amount of time to acclimatize to that reduced density and reduced oxygen content. But here also you will experience these kind of problems, and it also manifests in terms of my performance of my air breathing engines. So if I have a drone which actually is powered by an IC engine, when the density varies because of this high humidity content and everything, you may start experiencing power drop sometimes. So your power output for same throttle condition would be less, because this most of the smaller engines actually they are actually based on carburetor. So are you familiar with carburetors? What is the job of carburetor? Yeah, so it actually sets the ratio of your fuel and air. So now if my air has now more water vapor in that, which means more humidity, that would mean that my oxygen content has come down slightly for the same amount of air. So combustion will not happen properly. So what do I have to do? I have to maybe make my mixture less fuel intensive. So I have to maybe allow less fuel to come, so that I mean whatever oxygen I am getting, I can do a proper combustion with that. So you may have to adjust the needle slightly. If you have actually a electronic fuel injection system, EFI system, then this is taken care of automatically, because it actually takes care of the things. They have some kind of built-in curve and it senses the density or pressure condition, rather more of pressure, and based on that you will automatically do some things actually to correct for that. So that is the point. I mean, my actual ambient pressure, density or temperature may not directly conform to my international standards. So based on that, I mean, I can find an equivalent pressure altitude, equivalent density altitude and equivalent temperature altitude, which caters to what my international conditions tell. Okay. So this is a reverse way of looking at things. So you measure ambient pressure and look up at ISA table and find out the corresponding altitude, and this will be called as my pressure altitude. So I may be sitting in somewhere in Ladakh where I am at actually 3000 meters height, but my sensing may tell me that okay, I am actually at 2500 meters. Why? Because my pressure has changed to a certain value, and as per the ISA tables, that is what I get actually. So they often talk about this also. So pressure altitude, similarly density altitude, you measure the ambient pressure and look up the ISA table and find out the, sorry, this is actually a typo. This should be ambient density, because this is a density altitude. Okay. Yeah. But yeah, it is not very straightforward to measure density just like that actually. Okay. And temperature altitude, you measure the ambient temperature and check with the ISA table and find out the corresponding altitude, which would give you the same temperature. Okay, that is the whole idea. Now what is more common is the pressure altitude is fairly common, and sometimes you may come across temperature altitudes also, people may talk about that. Density altitude you will never ever hear, because you cannot measure density that simply. So there are not readily available instruments which could give you air density at a particular point. And
when we measure pressure altitude or temperature altitude, how do we say it? Like the pressure altitude is of this meters, or how do we?
Yeah. You will say that actually. So this is a kind of terminology which your aircraft pilots used to talk about. Okay. Because whenever they look at the altitude, okay, the altimeter just tells them the pressure. Based on the pressure and based on the ISA things, it will tell you the pressure altitude only. So they will always say, I am flying at this much of pressure altitude. Okay. So he may not know, I mean, geometrically at what height he is at, Purely based on pressure, he will say, okay, this is my pressure altitude, so I think I am flying at this height. Okay, so that's the whole idea.
But that could be problematic also. If it is.
No, because everybody is going to talk in the same terms. Right.
But then, if there are buildings which are.
So, I mean, that is a different thing. So, you will talk about AGL. See, when you are operating UAVs, you will always define your AGL, and that's why now people talk about, I mean, obstacle detection avoidance. So, if I am operating very close to our surface, there would be buildings, trees, anything, and that's where, I mean, this basic obstacle sensing, that, I mean, if I sense some wall or some building or some other obstruction, I will change my path or I will change my height. And sometimes, to be safe, people would know beforehand, so I am going to operate in an area and I know the terrain, I know what things are there around. I may have a topographical map also available sometimes. So, based on all that, I mean, I will plan my missions in a way that, I mean, I will not go and hit some obstacle. Okay. So, there are a lot of videos on YouTube where you can find old DJI Phantoms, okay, and old DJI drones. Whenever their battery would get low or the operator is giving them an RTL command, it is coming back and it will go and hit some building. Because RTL, it will actually, so later on in the later versions of software, they actually made it compulsorily that if you engage RTL, it will climb up little bit. So, go above say 40-50 meters and then start the return to avoid this kind of problems, because people are operating it and suddenly they will give an RTL. Now, in RTL, it used to come straight. Okay. So, wherever you are, I mean, it is somewhere else and it will just come in a straight line, and if there is a building or something, it will just come and hard. So, there are a lot of such videos of drones coming and hitting walls because of this RTL and this kind of problem. But these are very realistic things, because there is no other way of knowing your altitude very accurately. Now, with GPS can also give you height, but that is less reliable, especially the open channel ones. If you have encrypted thing, then your XYZ is very accurate. But what, I mean, you get as free open air GPS access, civilian GPS access, that is not very reliable. So, you are better off by relying on the, yes, I mean, depending on your local temperature conditions and so on so forth, it may try to do some correction based on these formulas and all, but it would still be approximate, it will not be exact geometric altitude. So, we normally deal with pressure altitude only, even in UAVs. Okay. So, what happens when you take off, you actually know the pressure altitude there, and that you reset to 0. So, then whatever height you go, you are always finding the difference. So, that becomes your reference point. So, you know, okay, approximately I have climbed up so much height, that is the idea. Yes. So, this I had mentioned earlier also. In India, because our temperatures are typically much higher compared to whatever ISA says. So, even in Leh Ladakh, you will go and you will find in summers, I mean, temperatures are very easily 15-20 degrees, 20-25 degrees also sometimes, which is, as per the ISA, it should be always close to 0 or negative or something, but that is not the case. So, depending on that, so whether you are operating in winters or you are operating in summers, you may have to give a reference condition which will be 15 to 20 degrees higher than the ISA, and we call this as Indian reference atmosphere. So, it depends, I mean, I have seen both kind of thing being done. So, a lot of times you will see these RFIs, RFPs, which would actually say that, I mean, we want this range of operation for our UAV, which would be able to operate from say minus 30 degrees Celsius to say plus 55 degrees Celsius, and then they will say this should be able to operate from this altitude to up to this altitude, like that. Okay. But they will normally specify, I mean, they will say, okay, if I want to do higher altitude operations, then they will say, okay, my launch altitude should be 3000 meters, okay, or 4000 meters, and then from there, I mean, I should be able to do 1000 meter AGL. Okay. So, they also use this term AGL. What does it mean? Above ground level. Okay. And other term was AMSL, which is above mean sea level, right. Okay. Yeah. So but they will say actually that, I mean, you should be able to cater to this ISA plus 15 degrees or ISA plus 20 degrees and so on. So, it is not a very standard definition in the sense that it is not, I mean, universally accepted thing. but for our convenience, because we know that the densities will be much lesser, and that is why we talk about doing hot and high trials. So, hot and high means the conditions in our high altitudes are actually low. I mean, the temperatures are expected to be low, but in reality in India their temperatures are higher actually compared to ISA, and therefore we say hot and high, which means I mean I want to test my UAV in summer in Leh Ladakh, which is a worse condition to test under. When you go in winters, the air actually is much more denser. So, you are slightly better off, your performance will be slightly better for your UAV compared to how it will be in summer. So, summer is the worst time at high altitude to test any aerial vehicle for that matter. Okay, so I will just introduce some very basic theoretical concepts. Again, this is a very basic touch up without going in the depth of any of these things. There are some definitions which would help you understand further concepts as we go. And of course, we already have talked about these three key governing laws or your fundamental principles. So, we actually sort of depending on the conditions we are operating at and depending on the kind of flow we are looking at, sometimes we treat the flow as inviscid, which means flow does not have any friction. So, viscosity part is actually not playing any role. This can actually be a reality when I have higher Reynolds number. Okay. So, when I go to higher Reynolds number, my inertial forces are more dominant compared to my viscous forces. So, that kind of flow can be sometimes considered as an inviscid flow. Other is flow with friction, which is called viscous flow. And so in the inviscid flow, my key approaches for understanding the fluid flow are the three key laws, which is the mass conservation law, my momentum conservation law and my energy conservation law. So, these are same thing which all of you have become familiar in your mechanics, in your physics, in your high school level at least for sure, and also in your first year undergrads, whichever discipline you were in, you must have been exposed to some of these things basically. So, we all know mass, momentum and energy conservation. So, momentum conservation is your Newton's law basically, right, Newton's equation, and energy conservation is your work energy principle, that work done should be equal to your change of energy, right. So, this is work energy. Okay, sorry. Right. And so, when I go to the viscous flow, I mean my mass conservation, which we call as continuity equation, still remains valid and fine, but this momentum conservation and energy conservation is not straightforward. Why? Because now it is equivalent to looking at a problem where friction is present. So, your energy conservation is no longer valid, because there will be energy loss because of friction. So, same way here I will have losses, and here what we say is that I mean we now look at these concepts of laminar boundary layer and turbulent boundary layer. What these are we will see little bit, let us see. So, we start with the basic idea of mass conservation. Okay. So, which means mass can of course neither be created nor destroyed except for relativistic things. When your particle or when your object starts approaching speed of light, then I mean your energy to mass conversion starts to happen, or rather mass to energy conversion, sorry, my bad, mass to energy conversion starts to happen, which is the famous equation by Albert Einstein, which is E equal to mc square, right. Okay. So, of course, we have not yet made UAVs which are going to fly at relativistic speeds compared to speed of light. We are only bothered with speed of sound for the time being. So, we are safe, we will not see our UAV convert into energy anytime soon. So, from that point of view, I mean for us my mass would not change, it will not get created or not destroyed. So, we are not talking about mass of the UAV, we are talking about the mass of the fluid which we are dealing with, okay. Because that is what actually affects all the forces over our UAV. So, the best way of looking at this, because this is the same concept which actually allows me to explain my change of pressure over my airfoil surface also, because when you enter the airfoil surface, initially you see some kind of this kind of converging duct, when you are going down you will see a diverging duct. So, that way your speed will change actually. So, mass flow rate m dot through an area A is the mass crossing this area A per unit of time. So, this is the first definition that we have to understand in this. So, it is just like, I mean, you open a tap and you see water flowing through that. Now, if the tap is connected to a tank, I can know after how much time this particular thing will be able to empty that, because if my pressure is maintained somehow and therefore, my mass flow rate is maintained at a constant value, then my mass flow rate into the time should be equal to my total mass of water in the tank, right. So, if my mass flow rate m dot remains constant, I simply have to take total mass divided by m dot. So, this m dot is rate of mass flow, at what rate mass is getting discharged. So, civil people will call it a discharge rate or something also, okay. But we will call it this mass flow rate, which is simply this. Okay. So, volume A into V is my volume change, okay, and rho is my density. So, rho into my volume will give me my mass and rate of change of mass with time. So, therefore, you have a term like V. So, rho A V equal to constant. Okay. So, which means if I create a conduit, or if I have my air or my fluid flowing through a duct for which my shape is actually changing at different points. Okay. So, if I look at that, so for example, in this case we see that my flow is going through this, and at the entry point I have area of cross section A1, my velocity of flow or the fluid is V1 and density prevalent here is rho 1. And then if I go to some other point with this let us say diverging duct here, and it is the cross section is increasing, I will actually have this same mass flow rate here also, which means my area of cross section has changed to A2. My density may or may not be same. I mean, if it is a incompressible fluid and my density is not changing, let us say water, then my rho 2 should be same as rho 1, okay, under all conditions. Even for air, my rho 2 and rho 1 could be same as long as my flow velocities are not very high. They are not getting into my high Mach number conditions above say 0.4, 0.5 Mach number, okay, when I mean compressibility has to be taken into more seriously. So, let us say if my density is same, my area cross section has changed. So, what happens now? My velocity is also going to change. So, if I assume constant density, so you see when the density is constant, flow is considered incompressible, which is what we will do mostly, because we are not going to design any supersonic UAV, I mean in or I mean near supersonic or high subsonic UAV for us, then I mean I do not have to worry about my rho changing actually. So, I will simply say this A1 V1 equal to A2 V2, which means if I increase the area of cross section, my speed will decrease, okay, and vice versa. If I decrease my area of cross section, my speed will increase. Okay. So, that is the very simple definition for conservation of mass, and this is the same idea which actually is creating my flow acceleration. Okay. So, if I draw my airfoil again, you see. So, if I look at this, right, if this is how my flow is happening, is coming through, right, this area you see there is a convergent kind of design, okay, which will immediately accelerate my flow here, and that is actually what creates my suction. So, that was the basic conservation of energy. Then we have conservation of momentum, which is basically Newton's law, but if I derive the Newton's law for fluid, it ends up becoming what is called as the 1D Euler's equation, which relates my pressure and my velocity field. So, here also I look at a cuboidal volume here through which my fluid is flowing, and so we have the cuboid has dimensions dx, dy and dz. So, on one side my pressure could be P, on the other side my pressure will change with P plus rate of change of pressure into the distance. Okay. So, that is what gives me. So, P plus dP by dx, because I am looking at the change across the x axis into dx, okay. That is my net pressure on this side. So, now law of conservation of linear momentum means force balance. So, what Newton said in his laws is that rate of change of linear momentum is equal to the applied force, right, or unbalanced force. So, that is what my unbalanced force could be F, and that I relate to this, and so this actually is same as mass into acceleration term, which here in terms of my, so mass means my density into volume. So, I get density into VdV, and this is called one dimensional Euler's equation. Okay. So, So, just like Newton, I mean Newton is considered a genius and he had contributed immensely. Another person of, I would say, similar stature and technical and I would say brilliance was Werner Euler. So, you would come across his name in multiple different disciplines and multiple different places. So, here we see his name coming as in a fluid dynamics, where he gave the equation for 1D fluid flow, inviscid fluid flow. And other place which you probably encounter in your +2 level mathematics is the famous Euler's equation. What is that equation? Yes, so this is not directly related to what we are doing here, but this actually is a very famous and very powerful equation. Then those of you who are doing structures course, okay, at some later stage you will come across something called Euler-Bernoulli beam theory. Okay. So, that is the same Euler, same this guy Werner Euler. Okay. So, we will come across his name in Euler-Bernoulli. Okay. Yet another place you will come across his name are the Euler's equations. And actually even before that, I mean before we come to equation, we talked about any UAV having 3 degree of freedom or 6 degree of freedom, 3 translation and 3 rotation. The rotational degrees of freedom we defined as the Euler angle. So, he worked on rigid bodies quite a bit actually. So, he defined these things, he talked about Euler angles to represent rotation, he talked about Euler parameters. Okay. So, I will again digress little bit just for your information, because this is also relevant for UAV, especially people who go and do controls and so on. So, I take any rigid body and I want to understand how would I define the rotation of my UAV from this orientation to some other orientation like this. So, at one point it is like this, other point it is like that. How would you define this change from here to here? So, one simple way could be that I can actually define it as 3 successive rotations about the 3 axes. Okay. I want to go from here to this other orientation, right. So, what do? I will say okay, okay, I mean it is oriented like this. So, I will first maybe say I will rotate it about x axis by so much, right. Then I will say okay, I will probably rotate it about the y axis about so much and maybe about the z axis by so much, right, and then I have reached the same orientation. So, depending on, so this is called successive rotation about different axes by using Euler angle kind of thing. But he was such a brilliant guy, he said that I mean okay, I can actually do this rotation in one shot. All I have to do is, so anytime I do a rotation of any rigid body, I have to talk about a pivot, right, a point about which I can do the rotation. So, normally if I take this, I can give it a pivot, so I can define these rotations very easily about this axis. But when I am doing this to this orientation change, how do I do that? So, he came back with this 4 parameter definition of rotations. Here we are talking about 3 parameters only, right. We are talking about okay, x 1 rotation, 2 rotation, 3 rotation, right, and I go from one orientation to another orientation. But how would you get this 4 parameter orientation? Anybody familiar with this? Have you heard of quaternions? What is quaternion? Have you heard of Euler parameters? So, this business of 4 parameter rotation is very ingenious, very brilliantly thought by Euler. So, he said that okay, I can actually to go from say this orientation to some other orientation, I can actually find an axis, some unit vector, I will find a unit vector about which I can go from here to here in one shot. So, this 4 parameter consists of the, so a unit vector which would have some a, b, right. So, he would say 3, so 3 parameters are basically defining the axis about which I will do the rotation, and 4th would be your some angle, some you could call it alpha, beta, gamma, whatever. So, these 3 parameters and this 4th parameter. So, with these 4 parameters I can uniquely define the change of orientation from one orientation to another orientation, and these are called Euler's parameters. Okay. He gave some theorem also about that and so on and so forth. So, all these stuff was done by same guy Werner Euler. And yeah, beyond this then he even went and defined the dynamics of the rigid bodies. So, just like Newton's equations gives you one part of the mechanics, the second part of the mechanics, which is the rotational mechanics, was done by Euler. So, which is a loosely one can write as sigma m, what is m? Moment, okay, moment, not momentum, moment, yeah. So, my unbalanced moment acting on a body would be rigid body can be written as where h is my angular momentum. So, when we try to define the flight dynamics of any aerial vehicle, we will actually be using these along with of course Newton's equation. So, three equations are your in translation come from Newton's equation sigma f equal to d by dt of p rather, which is linear momentum. So, one set of equation is f equal to d by dt of p, which is my linear momentum, and other set of equation, three more equations come where you said sigma m equal to dh by dt. So, this will give you the angular dynamics, translational dynamics, angular dynamics. Newton's equation gives you translational dynamics, Euler's equation gives you angular dynamics. We may get a chance to just briefly touch upon these equations before we finish our semester. Okay. So, fine. So, this is just to give you background regarding what is this, how I mean Euler has contributed immensely to several things, and Bernoulli who gave this equation. So, I am sure all of you are familiar with this. This is very basic example of how I apply conservation laws to fluids. I mean you are familiar with this because I mean we say okay, I carry a rigid body from here and keep it on the rooftop. So, I say mgh is my work done, or if I drop something from a height that actually has some potential energy which will convert back into kinetic energy. So, I will say mgh equals to some half mv square, right. So, that is one form of your thing for rigid bodies, okay. It could be rigid bodies or point masses or something, but for fluids where we are looking at pressure and volume changes, the same equation comes out to be in this kind of form. So, we have obtained this equation earlier that P plus dP plus rho v dV, if I because my energy is not going to change, I integrate that and I get that my pressure energy plus my kinetic energy, which is my, so this is my static pressure plus this is my dynamic pressure, it should remain constant. So, same idea I have applied, right. I mean for my velocity measurement also, airspeed measurement, right. Same Bernoulli's equation we applied there also. Now, interesting part is that this Bernoulli and the Bernoulli in Euler Bernoulli beam theory are not same person. So, these Bernoullis were all Italian merchants operating from near Venice area, and Euler was a family friend of these guys actually, and he collaborated with different Bernoullis to different things. So, Euler was one Euler, brilliant guy. Bernoullis were merchant guys and they had some interest in okay, so I like this thing, I like that thing. So, they are friends, and through other different Bernoullis he collaborated on this different stuff. So, this Bernoulli is some other Bernoulli from same family of course, but the Euler Bernoulli beam theory guy is a different guy. And finally, the speed of sound. So, this is the equation again comes from your gas laws and whatnot. So, R which we talked about earlier, I mean that is given as 287 joules per kg Kelvin, and gamma is your adiabatic constant which is 1.4 for air and common gases. So, if I plug in these numbers and take R as your sea level ambient condition 288 or something Kelvins, you will get A coming close to some 330 odd meters per second, which is a fair number. 330 is fine actually, okay, for our basic Mach number calculations and so on. But you can see now that my T is going to affect. If my T drops by 20 odd degrees, okay, I mean it will go from say 288 to it will go to say if I drop by 20 degrees it will come 268, right. Okay. So, you can see the square root of 288 versus 268, there will be a small factor which will modify your speed of sound. Okay. Not very critical, but if I am going at very high altitude and I see a very dramatic change in my temperature, then I must look at this, right. So, we are aware that I mean the NASA had been operating this Ingenuity aerial vehicle UAV, right, the first aerial vehicle to fly on a different planet. So, this helicopter had been flying there, and when they were designing this particular craft, they have to see what and how they are going to make it work there. Why? Because Mars has dramatically low density. So, the density at this your ground level on Mars is equivalent to Earth's density at 100,000 feet, 100,000 feet height, which is, I mean, 100,000 feet or 100,000, I think 100,000 feet, yeah, 100,000 feet, yes. Okay. So, 100,000 feet means, I mean, 30 kilometer plus, right. Okay. So that is the kind of density they have. So, it is a very, very rarefied atmosphere. So, now if I want to fly a rotary wing craft there, I mean a helicopter for that matter, it was a big challenge. So, you would think that, okay, my density is very, very low. So, what do? I would make my propeller rotor spin faster, right, which means I will increase my tip speed. But interestingly, the temperature there is also very low. So, my Mach number is much lower compared to what you see on Earth. So, if I go to higher tip speeds, I may very quickly reach a point where, I mean, I may be becoming transonic. Okay. So, that was not an option for them to really increase the tip speed significantly. So, that was another bottleneck which they had to really encounter to design this UAV. So, just, I mean, for your information, I just thought I will mention. So, this is what we use to find out the Mach number, and therefore, my Mach number is a function of my ambient temperature also. Okay. So, that I think completes this discussion. Any questions about this entire atmospheric business? Okay. Yeah.
Density, like density altitude. It's hard to calculate density at like high altitude. Why, sir?
No, not at high altitude. I mean, see, how do you calculate density of air?
Using the like temperature or the.
No, I can indirectly get that. I can indirectly calculate that.
Yes.
Fine. So, I will measure pressure. I will measure.
Yes.
I mean, but then what purpose it is serving to me?
We can calculate it, we cannot measure it.
We cannot measure it exactly. Okay. So, that is the whole point. See, I have to measure this. I can measure temperature. I can measure pressure. I have devices which can easily and accurately measure that. Okay. So, I have a pressure sensor which will give me it will act like my altimeter. I can have a temperature sensor, is a very common thing. So, I can easily measure temperature, but I cannot measure density. So, nobody will normally say, okay, I am flying at such density altitudes. He is not measuring it, he cannot get a reading for that. Yeah. And even temperature altitude people will not cater so much, more important thing is pressure. Yeah. That is what I mean matters more there. Yeah. Okay, so now we have reached a point where I can now give you first homework assignment. Okay, so tonight I will upload that on the Pingla portal and you can start working on that. So it will be due 1 week from today. Okay, so you can finish it and send it to me by I mean submit it in the class by next week. Okay.
So can we request for the slides?
Yeah, they are already uploaded actually on Pingla. Yeah, so all these are already there on the Pingla. Okay. Sorry, I am Hello ITK. Sorry, my bad. Hello ITK. Yes, of course. Yeah, I mean there are so many websites, so sometimes it's already uploaded there. Okay, so you can download it from Hello ITK. Yeah. I think this one probably not be there. So this I will upload after we have covered some part of it, but remaining things I have already uploaded. Yeah. Okay, so today I mean we will just briefly touch upon the basic concepts of flight mechanics. So far what we have done is that we have just tried to get very basic idea of what are the key factors in understanding and defining the aerodynamics of a fixed wing aerial vehicle. So, we looked at I mean the concept of airfoil, concept of wing, how a wing is different from an airfoil, the mechanisms of generating lift, drag, pitching moment. Very briefly we talked about how the different airfoil tables can give you hint about which airfoil should I select. Yeah, and the idea of L by D. Now, we kept talking about I mean that I want to maximize L by D, but why? We did not really give a definitive argument or a proof to say that I mean L by D is important for me. It does look intuitive that yes, I mean I would really want to have more lift and less drag, which means if I do L by divided by D, it automatically gives me a parameter which if I try to maximize, I am automatically trying to get higher lift for every unit of drag. So that actually is a very loose argument which we used, but now as we go into the basic flight mechanics aspect, when I say flight mechanics, we will primarily be looking at the performance aspect. So, I want to find out, I mean, how much of energy my UAV is going to consume for a flight, how much of power it is going to consume in a particular flight, how it is a function of my overall weight of the craft. So, all these basic ideas we will look at. Okay. So, people who are coming from aero background, they are already familiar with this, but we will have a quick revision, and for those of you who are not from aero background, it is something which you have to understand. Again, here we will not go in tremendous depth, we will try to basically understand the overall idea of different forces which are now acting on the whole aircraft. So, we looked at the wing, but that is not the entire picture. Yeah, I have to understand how my entire fixed wing uncrewed aerial vehicle is going to operate and how its different parameters are going to affect its overall performance. So, this is a very simple sketch of a fixed wing aerial vehicle, and we try to understand what are the different forces which are acting on this craft. So, here I am only talking about the whole aircraft as a entity. I am not trying to say that the lift actually is coming from wing, it is the net lift which is combination of the wing plus body. So, there is the idea of wing plus body lift. Okay. Similarly, the drag also, I am not worried about the drag of my wings alone, the drag of the entire aerial vehicle. Okay. So, my lift we say wing body lift, drag also we will say for the same wing plus body drag. Okay. So, I have lift acting normal to my direction of airflow, which could be in this direction. So, this is my direction of V infinity of free stream. Okay. So, I have lift, I have drag, and of course, the whole aircraft will have some weight, because that is something which my lift must balance to keep it flying. So, my weight will be acting vertically downwards, and now there are certain angles which are also being shown. So, this is my horizontal line, and my craft is having a velocity which is making certain angle with the horizontal. So, that particular angle we call as flight path angle. So, I am just bringing in some definitions here. What is my T here? So, this is the thrust which my engine, my propeller plus motor combination, or propeller plus engine combination, or if I am using a jet engine, that is all it. So, this thrust has to be supplied by some power plant, right. So, this is thrust supplied by my choice of power plant, right. And the wing and the overall aircraft may be oriented at certain angle of attack, and that is my alpha is angle of attack from the chord line of the wing per se. So, from this one can clearly see that my lift should approximately balance my weight, and my thrust should approximately balance my drag. This is required to ensure my UAV is flying in steady level flight. Okay. Okay. So, these are the things which we already talked about: lift, drag, weight and thrust. So, if so this is like a free body diagram, okay, and I have all the forces and moments listed here. So, I can resolve them about different angles and write the equilibrium equation for this, again by using conservation of linear momentum, which means by using Newton's equations. So, all the forces which are acting in the horizontal direction, right. So, I can call this as x axis and I can call this as y axis. So, doing the force balance along x axis, what are the forces which are there? I can see T and theta plus alpha. So, T into cosine of theta plus alpha. So, here we are only seeing alpha T because for steady level flight, if I am not climbing, my flight path angle would be 0. So, we are dropping that right away. So, theta is flight path angle. So, if my aircraft is not climbing and is in steady level flight, this theta is 0, okay, which means my horizontal and this are same basically. Okay. So, this angle is 0. So, then what happens now? The forces which are there in the forces along x axis. Okay. So, that will be my T, I am sorry,
E equal to D.
What is theta? Sorry.
No, sir. The thrust and drag averages.
Yeah. No. So, that actually will come, but yeah. So, right now we will take everything in the horizontal direction. Okay. So, which means T into cosine of alpha T, that is a component of that. Similarly, drag has the same angle. So, it will be minus of D into cosine of alpha T. Okay. So, these are the two things which are there. Yes, and W also. Okay. Now, the theta is 0. So, this is 0. So, W is actually straight vertical. So, I get T cos alpha T. Oh, okay. So, this actually is assuming that my drag is actually along the horizontal. So, sorry, this is actually along the horizontal direction, this is along this line, and T is actually, so my wing is at a small angle of attack and my propeller is oriented on the wing. So, my thrust is actually not along the horizontal path, it is actually along the direction of the wing, okay, not flight path, it is actually at an angle of attack. So, it is like, see, my wing is actually like this, right, and this is my horizontal. So, my flow is in this direction V infinity. So, my drag is actually in this direction, I mean the other direction actually. Yeah. So, this is the direction for D, and this is my angle of attack alpha, and my propeller is actually mounted here. So, my thrust is along this direction. Okay. So, normally we will mount propeller on the wing, and it is mounted normally. So, whatever angle my wing has, the same angle my propeller also has. So, that is why this T has actually this angle alpha T, but my drag actually has only D. So, D is actually in the, so D is now, once my this angle goes to 0, my D is along this direction actually. Okay. So, T cos alpha T minus D, and well, if alpha T is, so this actually is probably not entirely correct, because theta should have been added into this if I wanted to resolve it along. So, this will say it goes to 0 because my theta has gone to 0, and W is actually this goes to 1 basically. So, my simplified equation, so this actually should be equal to, okay, this is also a typo, it should be M A tangential and this should be M A normal. So, I am resolving all the forces in the tangential and the normal direction. Tangential means along the horizontal direction, normal means vertical direction here. Okay. So, this should actually be equal to mass into acceleration in the tangential direction and mv square by rc in the normal direction, assuming my craft is actually doing some kind of maneuvering flight. But if it is in a steady level flight, for steady level flight with small angle assumptions, first of all, steady means my speed is not changing. So, this goes to 0, okay. And level flight means I do not have any tendency of going in a climb or going in a pull up or going in a pushover. So, I am not doing any of those maneuvers, which means my centripetal acceleration is also 0. So, this actually is coming from, so this is actually centripetal acceleration m into a tangential, which would only be there when my aircraft, yeah. So, if this is the aircraft, it is actually in a say circular vertical loop, it is trying to fly in a circle like this, okay, in a vertical plane, or if it is actually doing a turning flight. So, whenever you try to go in a circular trajectory or a path, you will always have some amount of centripetal acceleration. The reverse of that actually is called centrifugal force, which is not really a force, it is actually a pseudo force. You just sort of bring in to negate this acceleration. So, when you want to, instead of using Newton's equation, I want to use D'Alembert's principle, where I apply a pseudo force to give you a static equilibrium kind of scenario. But in reality, it is actually an acceleration which I should model it on the as the acceleration part. So, if I use Newton's equation, I will write it like this only. Okay. So, all these are 0 and my angles are small, my alpha t would be 3 degrees, 4 degrees. So, it is a sin alpha 3 degrees is close to 0. So, I simply come down to this very simple equation, where my lift equals to weight and my thrust equals to drag. Okay. And this is very simple, but this is the building block of all my basic performance calculation and so on. Okay. So, I think we are out of time. So, let us stop here, we will continue from here in the next class. Okay.